Thank you very much, Rodrigo. Yeah, thank you for all the organisers for having me to talk about the work we've been doing in WISDOM in measuring supermassive black holes in galaxies across the Hubble sequence. So this is work that we've been doing for some time with a reasonable sized team of us. So there we go. So here's a picture from our recent meeting. You can see some of the people here, and there's also various other people, some of whom are with us today from outside our team who've collaborated with us on various parts of this. So there's lots of postdocs and students been involved. So this work is all due to them. So thanks for that. So everyone here cares about black holes. We all bothered to turn up today. And so far, we've mostly heard, because it's early in the conference, about high redshift. But my interest in black holes is mostly based on their impact on the galaxy properties that we measure at low redshift. So in understanding AGN quenching, essentially, we know that in order to produce the galaxy population we see around us in the universe today, we have to have some form of energetic input from black holes. No simulation of the universe in recent years has been able to do without this in order to get the sort of quenched massive galaxies and to stop the overcooling problem in massive galaxies. And so it seems that black holes provide this wonderful reservoir of energy that we need to actually get the galaxy properties we see around us today. So they seem to be a crucial part of our galaxy evolution paradigm. But our observational evidence is still lagging a bit behind. We see, for instance, AGN-driven outflows. We see in clusters the impact of AGN and offsetting cooling flows. But what we really lack is the evidence on the small scales of how this process is working in individual galaxies, with a few exceptions. So one thing that really motivates the work that I'm doing is, can we see the integral history, the evidence that these black holes are involved in quenching? So if you liberate a lot of energy using a black hole, it has to accrete, so it has to grow in mass. So you would expect that black holes in galaxies, which are quenched and have been quenched by their black hole, that those black holes would be larger at fixed other galaxy property than galaxies that are currently forming lots of stars and their black hole hasn't been involved in a large quenching episode. But this is really hard to study. It's been seen in simulations. This is a correlation that's predicted to exist in all of the simulations. But it's really hard to study observationally. And this is shown very nicely here by this paper from 2013 by McConnell and Ma, where the different points here are all dynamically measured supermassive black hole masses plotted against the velocity dispersion of their host galaxy. And the little symbols, so the stars, are measurements that have been made using stellar kinematics. So we saw a bit of that in Anil's talk. Then gas or ionized gas kinematics have been used in all the round points. And masers, so these microwave lasers that shine in the accretion disks of around typically safer spiral galaxies, are shown in the triangles. And you can see that the red points are all, and the green points are the early type galaxies, the blue points are the late type galaxies. And you can see, for the most part, there's not a lot of overlap in the samples. The stellar kinematics have been used for most of the early type galaxies, with some ionized gas measurements. The masers and the gas measurements dominate in the spiral galaxies. So that leaves you very susceptible to systematic effects when you want to study this type of effect. So in McConnell and Ma, they show here that they do have an offset between their spiral and their late type galaxies. But given the error bars on the points and the systematics, it's hard to know whether this is really encoding this history of quenching or it's just related to the techniques. So we want to expand our toolkit, and we want to be able to measure black hole masses across the Hubble sequence in the same way, ideally, and also for very low mass galaxies, if we can, to really anchor the relations. So we need to find a tracer or a method that we can use in all of these places. So as you've already heard, molecular gas provides an excellent way of doing this. So why is it so good? So if you want to describe an ideal tracer for estimating dynamical black hole masses, you'd want it to be dynamically cold in all galaxy types. So you want it to be just rotating, following the potential of the galaxy. So you don't have to model in lots of complicated dispersion, supported kinematic components. You'd want it to be present to the very center of the galaxy, so you can trace that nice Keplerian part of the rotation curve around the black hole. And you want it to be observable at high angular resolution. That's obviously crucial to be able to resolve those areas. A molecular gas meets all of those things. So you may say, well, spiral galaxies definitely have molecular gas, like this beautiful one on the right-hand side here. But early type galaxies are supposed to be red and dead, right? But that, as you've already seen in Ben's talk, is not always true. So about 25% of early type galaxies have molecular gas reservoirs. And often, as you've seen, they're in these circumnuclear disks that are very nice, regular, and relaxed. And the work that we did on this as part of the Atlas 3D survey, for instance, among others, and that I've been doing as part of the Massive survey, have shown that this molecular gas is present in these early type galaxies essentially independently of their other properties. It's a mostly accreted gas that's been brought in since the galaxies were quenched. And so those processes to 0th order happen independent of your other properties like the mass of the galaxy, for instance. So this material can provide a tracer. It's not in all of the galaxies, but it can trace a fairly independent population across your black hole galaxy populations. It's also a very cold gas. It's at 10 Kelvin typically, so it has a very low velocity dispersion. It's dominated by the intra-cloud component. So it's about 10 kilometers per second velocity dispersions. That's much lower than your typical ionized gas velocity dispersions in the center of galaxies. And with ALMA, you can reach very, very high resolutions. So I put 10 milliarc seconds here, but you can even push that further if you're willing to use a higher transition of the molecule. From the ground, and you just put your telescopes further apart, you get a better resolution. So it provides all of those sort of ideal requirements that we would want. So this is why we started WISDOM. So it's the millimeter wave interferometric survey of dark object masses, because everyone has to have an acronym. And the idea of this survey is to calibrate this technique and use it to tie down these black hole host relations across the Hubble sequence. And of course, we have beautiful data on the centers of these galaxies. And so there's lots of other things you can do, and I'll highlight that at the end of this talk. So how does it work? You've already seen this a bit from Ben's talk, so thank you very much, Ben, for the really nice introduction. So I don't need to go too slowly over this, but this is an example. So this is an elliptical galaxy here, NGC 383. It's actually a 3C radio galaxy with a large radio jet, so we know it has a big black hole in there that's accreting. And if you look at it, you zoom in, so this is an HST and Chandra combined plot here. So you see this dust disk in the center. That is one of these circumnuclear disks that these galaxies often host. And you also see in the Chandra image the jet base. So you see this big jet being launched from this galaxy. So this galaxy is actually mapped previously by a kind of Flackera, 2010, with the Plateau de Boer interferometer. And you see that there's molecular gas in this disk, but at the resolution available with PDBI, it wasn't particularly resolved. So with ALMA, we can do much better than that, of course. And so a PhD student who was working with me, Eve North, went and obtained these beautiful observations of this circumnuclear disk in this galaxy. So this is 0.1 arcsecond data. That's about 40 parsecs at the distance of this galaxy. And you can see it's a beautiful regular disk with some spiral structure overlaid. It's not as asymmetric as PDBI seem to see, but that's all down to your coverage of your interferometer. So with this beautiful data, the beam of this, the synthesized beam, so your PSF is shown in the bottom left hand of this panel. You see we super resolve this supernuclear disk, so we get very nice kinematics. So these are shown here in this panel. And for those of you with eagle eyes, you can see already that there's a very high velocity gradient right in the center of this galaxy, right where the supermassive black hole would be expected to live, based on the continuum emission, for instance, that arises right from the center of this disk. And indeed, you can see this a bit more clearly if you extract the position velocity diagram. For those of you not used to working in the optical, this is essentially you lay down a pseudo long slit along the major axis and you extract the kinematics, as was also seen in Ben's talk. And yes, you can immediately see, if you extract this, you can get the Keplerian rotation around the black hole in the center of this galaxy, and then the emission that's dominated by the stars further out, where the rotation curve is approximately flat. It's still actually rising in this circumnuclear disk. So you can very easily separate out the black hole signature from that caused by the stars, and you get a very accurate black hole measurement, pretty much independent of what you do about the mass to light ratio, for instance, of the stellar population, which you can also constrain with these observations. Of course, it's not as simple as all of that, because we have a data cube observed with an interferometer in Fourier space. So there's all sorts of beam effects, interferometer effects that need to be carefully treated. So for that, I developed this code called Kinemess. It's an observation simulation tool that you can link with Bayesian inference code in order to directly model your observations. And also you could use it for observation prediction and various other things. So it's described here. It's available on GitHub, or you can pip install the Python version if that's your coding language of choice. So that's out there, and I encourage you, if you're interested in this sort of thing and it would be useful for you, please go have a look at that, and feel free to drop me any questions you have about it. Happy to help you with running it and using it. So with this Kinemess tool, we can complete a full modeling of the data cube to find our best fit parameters in a Bayesian framework. And we include information on the stellar potential. And we do that via modeling of the Hubble Space Telescope images to get stellar light distribution. Obviously, we have to include the dust correction that was mentioned is very important in Ben's talk. And that gives you your stellar mass distribution modulo a mass to light ratio, which is a fitting parameter in our modeling. So that's obviously an early type galaxy. Those have had a lot of black hole masses measured in them before. And we can't just complete our ideal of measuring galaxies' supermassive black hole relations and how they change with morphological type just with early type galaxies. We need to push beyond that. So with WISDOM, we're really also targeting spiral galaxies and other galaxies in undersampled regions of the black hole mass galaxy property planes. So for instance, spiral galaxies. So here we've got a beautiful SA galaxy. We don't detect the Keplerian rise in this case, but we do detect a clear excess in the rotation over and above what we would expect given just the stellar potential. And you see at the bottom right hand is the molecular gas image of this when you go to 10 parsec resolution. So you're really resolving individual molecular cloud cores here. That's why it looks a mess, like a noise field, but it's not noise. Those are individual resolved giant molecular clouds in a galaxy, in this case 50 megaparsecs away. So we can also measure black hole masses in these spiral galaxies, but not just spiral galaxies. We can also push and observe dwarf galaxies. So this is an example. This is a galaxy that was also featured in Anil's talk earlier, NGC 404. It's a dwarf elliptical galaxy just outside the local group. And you can see in this ground-based image and also in the HST blow-up of the center, there is a flocculent dust disk around the center of this object. So we went and we observed it with ALMA, and we had some information on the molecular gas properties before based on this 2015 paper by Taylor, Petipas and Rio that has 7 arcsecond resolution obtained with BEMA. And you can see essentially it's a point source of those ratios. But if we take ALMA, we can observe this now at very, very high angular resolution indeed. And this is just the very center of the map we get here. So you can see this is a half parsec resolution map of the gas in the center of this nearby dwarf galaxy. It's got a stellar mass of about 10 to the 9.1, so it's relatively low mass. And you can see this wonderful flocculent ring structure with this arm that goes into the center, wrapping around a circumnuclear disk right at the very, very center, or a torus structure almost, at sort of 1 to 3 parsecs away from the black hole, at the very center of that eye-type structure you see in the middle of this field.
In 5 minutes.
The kinematics, thank you. The kinematics of this can be modeled. So again, we extract the pseudo long slit. We actually fit the data cube in this case, but the pseudo long slit allows you to see this very nicely. And you can model this kinematics with Kinemess. and get a beautiful fit that retrieves a mass of 5 by 10 to the 5 solar masses for this black hole. And in this case, this is a little bit higher than was measured previously using ionized gas and stellar kinematics. And the reason is that actually the molecular gas in this galaxy is important to the potential. And so if you include its effect, you need a lower mass to light ratio, and so that pushes your black hole mass up. So often in cases like this in low mass galaxies, but sometimes in high mass and spiral galaxies, you need to include this molecular gas component in your mass modeling of the galaxy. Otherwise, you're going to get the wrong answer. And I think that's crucial and another good motivation for going out and getting these sort of maps. So this is, obviously quite a low mass black hole. It's well below 10 to the 6 solar masses. So some people call this an intermediate mass black hole, some people don't, but it's clearly very low mass and helps us anchor those black hole property relations. The really nice thing with these ALMA observations is that they're going to be possible in a lot of galaxies in principle. So in this paper here, so this is from, I didn't put it on the slide, I should have done, this is from a paper by myself in 2014. This shows the mass of black hole we can resolve the sphere of influence of at a given luminosity distance or redshift on the top axis. So you can see the known galaxies with black hole mass measurements are the points, and the known upper limits are triangles. So you can see that we could redo basically any of the measurements that have already been taken. And at higher redshifts, we can still probe a large fraction of the galaxy. Hundreds of thousands of the SDSS galaxies, which are the gray shaded regions there, are accessible with ALMA. And the most really interesting thing is that if you go to a black hole of 10 to the 9 solar masses, ALMA would allow you to resolve its sphere of influence at any redshift because of the turnover of the angular diameter distance with redshift. Of course, you have surface brightness dimming and other effects that could stop you measuring a black hole mass or detecting the galaxy in the first place. But in principle, if you have bright gas around a galaxy, you could probe it with this technique. So I think that's its strength. So what have we managed to do with this technique so far? So here we show, I show the black hole mass velocity dispersion correlation now. So this is from Van der Bosch, the compilation of Van der Bosch. There's been more recent ones, but I haven't had time to update my plots yet. And the red points here are black hole mass is measured with this molecular gas technique. So from our Wisdom survey, from Ben's surveys that he was talking about before, and some others, all compiled together. So there's 18 measurements on here, including some that are in prep from our team. And you can see we're really starting to probe black holes along the whole range of the M sigma relation, right from NGC 404 that I showed you at very low masses, right the way up to the very most massive black holes above 10 to the 9 solar masses. So we can really start to sample these. If we look at the black hole mass bulge mass correlation, you can see that we're able to add quite a few here compared to the ones that are already known. So there's a lot of promise with this technique, and we're starting to fill in areas of this plane that were fairly undersampled before, especially by the spiral galaxies that sit at bulge masses of 10 to the 10 or so on here. So just in the very last couple of minutes, Wisdom isn't just a supermassive black hole mass survey. So with our observations, we typically reach 10 or 20 parsecs in the centers of 40-ish nearby galaxies. And so we can get a lot more than just black hole masses. So we can look at the ISM physics deep in the bulges of these galaxies. So we've found that the clouds, the molecular clouds in these regions feel the deep potential that they live in. And this changes the properties of the ISM. We can also look at AGN feedback. We've got a couple of molecular gas outflows that we've seen being driven by the AGN in these systems. And also we can look at AGN fueling. And I know this is a black hole conference, and so we probably mostly care about that. So won't really talk any more about these in the last minute or so, but just present some work on the AGN fueling that's about to come out or about to be submitted. So we can look at exactly what's fueling the black holes in these galaxies. So for instance, this here is a spiral galaxy or a spiral galaxy core. It's actually a luminous infrared galaxy. So it's very highly star forming. And it's got a strong Seyfert AGN in the center. And our observations resolve the molecular gas in its center very, very nicely indeed. You can see on the right-hand side here. And when we look at the kinematics, we find that we can estimate the black hole mass very nicely. It's about 10 to the 8 solar mass black hole in this case. But we can also see that the kinematics reveal an inflow. So the middle panel here, so on the left-hand panel of this plot, you can see the rotation curve extracted for this galaxy with the rise caused by the supermassive black hole in the center. In the center, you see the radial velocity that's required to match the data cube. So at large radii, there isn't much inflow in this case, but at low radii, below about an arc second, we see an increasingly speedy inflow of material flowing onto the black hole. We're able to tell its inflow because we know which side of the galaxy is which. And you can model this, and you find that you've got about 8 solar masses or 7 solar masses a year of cold molecular gas flowing inwards at about 70 kilometers a second towards the nucleus of this galaxy. And this is likely what's fueling the very strong AGN in this galaxy and fueling its black hole. So with this sort of data, we can get this sort of information on galaxies across the Hubble sequence with all types of AGN. Our sample covers jetted AGN, non-jetted Seyfert, and inactive galaxies as well. So we can compare these sort of inflow properties that we detect that are quite subtle and hard to detect without this sort of data. So I imagine I'm just about out of time. So the conclusions then is that WISDOM is bringing us, and of course the measurements presented by other people like Ben, this technique is coming of age. We can reveal the black hole mass properties across the Hubble sequence. Lots of galaxies are accessible using this technique, although we do still need, of course, stellar mass models. So we still need HST or JWST or AO to complement our observations. And we also get a lot of information on the host galaxies as well, like the ISM physics, AGN accretion, and feedback. Thanks a lot.